and do our second from 1.3. And we're going to start talking about the ratios for our common angles. How do I stress this enough? That these two different triangles we're going to show you and the ratios that come from them, how important they are. I'm not sure if there's anything in the whole class I would want you to know more than this, getting out of the class. This is just so fundamental. You're essentially guaranteeing not being able to do problems later by not knowing these common angles. We use some ratios for these common angles. Let's see what we mean by it. So we're going to build some stuff. Here's two different triangles. They're the same type of triangle. I just have one written. On the right is in radians, and on the left is in degrees. So what I'd like to do here is I'm going to mess with the one on the left, and I'm just going to give one of them a length. I'm only going to mess with it, and I'm just going to say that I want the hypotenuse to be 2. Okay? Cool. Cool. I'm going to build something out of it. So if that's true, we're going to say that there's A and there's B. But if they're both opposite 45 degrees, what do you think is going to be true? If they're both opposite the same angle, won't A and B actually be equal to each other? Yep, it's true. So if we go to use our SOHCAHTOA, not SOHCAHTOA, but our Pythagorean theorem, I've had A squared plus B squared is equal to our C squared. Well, let's replace in. Well, let's just leave A as A. But let's change B into A, so we just have one variable. And then we'll change our C, which is 2. There we go. So it looks like we have an A squared plus an A squared. So I think that gives us 2 of those A squareds, right? If you have something plus the same something, you have 2 of them. And then 2 squared is 4. And let's isolate that A squared, so we'll divide by 2. So A squared is equal to 2. And then let's hit both sides of this equation with a square root. So we get A is equal to the square root of 2. And if A is equal to the square root of 2, then B is also equal to the square root of 2. So let's replace. And here we go. We have a cool little triangle here. Well, shoot. The reason why we're doing this is we want to know what sine of 45 degrees is. We want to know what cosine of 45 degrees is. We want to know what tangent of 45 degrees is. That shit pops up all the time. 30s, 45s, and 60s. Pi's over 6s, pi's over 4s, and pi's over 3s pop up all the time. We gotta know them just on lock. You can't be looking this shit up constantly. You just gotta know it. Alright, so if we look at our triangle, we're like, well, let's go find sine of 45 degrees. And not like it matters, but I'm gonna look at it this one. So our opposite is right there at root 2, and our hypotenuse is here at 2. Right? That's what it is. So coming out of that one, we're going to say that this is equal to root 2 over 2. Neat. Cosine of 45 degrees. Well, let's look. We're going to get our adjacent over our hypotenuse. And we also get root 2 over 2. Oh, weird. And then we have tangent of 45 degrees, which is just our opposite over our adjacent. So that's root 2 over root 2. So root 2 over root 2, well, same picture over same picture is 1. Huh. We now know the ratio for sine of 45, cosine of 45 degrees, and tangent of 45 degrees. We can start solving some triangles now. We can do some shit. Cool. I highly advise memorizing this little triangle here. Or, if nothing else, just getting this dialed in. Should I help you have both? Cool. And we could have wrote this as sine of pi over 4 is equal to root 2 over 2. Cosine of pi over 4 is equal to root 2 over 2. Because the angles are inside the trig function, and they spit out a ratio. Cool, let's go to another. Hey, uh-oh. Wait a second, that's not a right triangle. Well, if they all have an angle of 60 degrees, well, shoot. Don't they all have the same sides? They all have the same. This is what we call an equilateral triangle, right? So this is, I'm just going to give them all a side. I like 2. 2 is good. 2 is a good number. It's not as cool as 1 or 0, but it's a pretty good number. So we're going to play a little trick. We're going to play a little game. I want to create a 30, 60, 90 triangle. 30 degrees plus 60 degrees is 90, so that's going to work out well. So the way we're going to do is we take an equilateral triangle. Nah, I don't want an equilateral triangle. I want a right triangle. So we'll do something called dropping a perpendicular. We just drop the perpendicular. And since they all have the same side, we could actually take this 2 and realize that, oh, this is 1 and this is 1. So if we just look at the triangle in blue that's on the left, I'm creating now, we've now created what's called a 30, 60, 90 triangle. Because this has to be 30 degrees. Because the other two angles of a triangle must be complementary. The sum of the interior angles of a right triangle have to add up to be 180 degrees. Actually, all triangles, all two-dimensional, including triangles. So let's draw our triangle off on the side. A little scaled down version. Just the left-hand side saying 60, 30. We have the 2 and the 1. Well, it looks like the only thing we need to do is go find that opposite from 60 or the adjacent from 30, depending upon how you want to look at it. Wow, this triangle, I think, gives us a little bit more information. So why don't we start off with sine of 60 degrees. And we're purposely ignoring the reciprocals for now. So we're looking from 60, and we go, all right. Oh, dude, we need b. Dang, right? Because the opposite's b. We have to do that Pythagorean theorem. We got to go solve for b, or our opposite. So we say a squared plus b squared is equal to c squared. So 1 plus b squared is equal to 4. Subtract the 1s. B squared is equal to 3. And let's hit it with a square root on both sides. We ain't got to trip about plus or minus because everything is positive because we're dealing with lengths. And there we go. We found that other side. Oh, no, that's ugly. Root 3. Yuck. You are going to be very comfortable with that number, root 3. So we solve for it. Now we can go find all of our ratios. Sine of 60 is our opposite, root 3, over our hypotenuse, which is 2. Cosine of 60 degrees. Well, that's just going to be our adjacent over our hypotenuse, which is 1/2. And then tangent of 60 degrees. Well, shoot, that's going to be our opposite over our adjacent. So root 3 over 1. I'll write over 1. You don't need to do that. It's just root 3. Cool, we got our 60 degrees. So now we know how to find sine of 45, cosine of 45, tangent of 45. Now we can find sine, cosine, and tangent of 60. And shit, let's just look. Look, my voice is cracking and everything. Let's go get sine of 30 degrees. Shit, we're here. We might as well. Well, let's look. What's the opposite from 30? That's 1 over 2. So sine of 30 must equal 1/2. Oh, weird. That's what cosine of 60 equaled. Huh. There might be some sort of theorem. There goes my dog. So cosine of... Oh, why did I write 60? Not 60. I was thinking about that, huh? I was thinking about that. Cosine of 30 degrees. So we're still coming out of this. 30 degrees. So we have our adjacent over our hypotenuse. So this is root 3 over 2. Oh, weird. That's the same thing as sine of 60. Sine and cosine. They're actually called co-functions. Looks like complementary angles of co-functions are equal. Well, whatever, moving on. And now we have tangent of 30 degrees. We're like, what's that going to be? That's going to be our opposite from 30 over, so that's 1 over root 3. And I like that answer better. I don't even like the root 3 over 3. That pisses me off a little bit. I like 1 over root 3. But if you rationalize this thing, it's the same thing as root 3 over 3. I personally prefer it as 1 over root 3, but you will find this in your text, and I know they're going to have you rationalize. So what did we get to? What did we find out? This is what we found out. That sine of 30 is equal to 1/2. Or we could just use these triangles to find out that sine of 30 is equal to 1/2. So you can either memorize this table or you can memorize these different triangles. Cosine of 30 is equal to root 3 over 2. Tangent of 30 is equal to root 3 over 3. We just did those. But what you need to be comfortable with as well is saying sine of pi over 6 right? Because 30 degrees and pi over 6 are the same thing. I don't show you with radians because I'm trying to get you to understand at the beginning, so I'm using degrees. But soon I'm not going to give a shit whether you understand about it. This beginning, I'm trying to get you to get it. Soon, we got to start throwing those radians in there, and that's going to start jacking our brain up a little bit. All right, so we have everything. These are all the same. These are in your textbook. You can look them up as well. Sine of 45 goes with your root 2 over 2. Root 2 over 2. Weird. Okay, so there's all of our stuff. Now, I have a table that I typically like to write in, so I'm going to show you. Just move down. And take it or leave it. Oops. I got some small pen. All right. So this is a little table that I make. Go away. Go away. Go away. And I'm going to put in just a couple of angles here. 30 degrees, 45 degrees, and 60 degrees. So what I'm saying is this is, you're going to plug 30 degrees into sine. And we're going to get an answer. So sine of 30 degrees is equal to, is equal to 1/2. The square root of 1 over 2. Sine of 45 degrees is the square root of 2 over 2. Sine of 60 degrees is the square root of 3 over 2. Cosine of 60 is the square root of 1 over 2. Cosine of 45 is the square root of 2 over 2. Cosine of 30 degrees is equal to square root of 3 over 2. Now I'm going to put in a couple of things, and I'm not going to explain necessarily why yet. 0 degrees will be 0 over 2. Cosine of 0 is equal to 1. 90 degrees. It shouldn't make any sense because these aren't triangles. So just bear with me. This is going to be 1. Sine of 90 degrees is 1. Cosine of 90 degrees is equal to 0. So if you look, check this out. Same answer. Same answer. Same answer. Same answer. They're just going opposite directions. They're moving in opposite directions. So if you could actually just get this table, this little teeny table down. In class, I would have shown you this and then quizzed you the next day on it. I would have brought you in, had this table, and just said fill it in. If we were in class. But we're not in class, so I can't really play these games with you. I would force you to understand this over and over and over. I would just beat it like a dead horse, trick you into every different way I could of trying to memorize this thing. I'd give you quizzes like crazy, pop quizzes trying to get your brain to get this all memorized. But since we're online, I can't play a lot of those games. All I can do is beg you to learn this. And you're like, why? I could just have it written down. All right, cool. Cool. Don't. Struggle with this all the way through calculus and through physics. This little table is, oh my gosh, it's a hookup. And I'm going to show you a whole host of other ways to get this stuff memorized as we go. There's something called the hand trick. There's some other stuff that we could use as well. But that's for another day. So there's the beginnings of our common ratios. I would use these triangles, either get these triangles memorized up. We use them. It's just something to reference back to. We actually call these reference angles, 30s, 45s, and 60s, or pi's over 6s, pi's over 4s, and pi's over 3s. All right, well, I will see you in the next one, and we'll start messing around with a few more of our identities. See you.